Now, many a times in the question, you would be hearing the word massless, the expression massless pulley or frictionless pulley. Now, we'll discuss what this massless pulley means and what the frictionless pulley means. If the pulley had a mass, what will be the effect? If it had friction, then what will be the effect? So, now coming to first the word frictionless. Now, suppose if the pulley is frictionless, then whether it is having mass or not, and it's a fixed pulley suppose, then whether it is having a mass or not, it is not going to matter. In fact, I've drawn two situations. There is hardly any difference between the two situations apart from the small angle over there. So if you ignore the angle and it is almost a flat string, then if the surface is frictionless, then the tension this side of the string and the tension that side of the string is going to be same. If there was friction, then what happens? Depending on which way is the tendency of slipping, the friction acts and the tension on the two sides are not same. So when we are discussing friction and the tendency of which way the friction is acting, then we will debate more on whether T dash is more or T is more. Or let me ask you, if this body is going down, what do you think? Which one will be more? T dash or T? So if the body is going down, the friction will have a resistive action over here. It will resist the thread from going and it is going to give a backward force on the thread this way, which is going to increase the tension and which is going to decrease the tension over here. It is going to force the thread that way. Means if you imagine the thread to be an elastic, it is the force on the thread is towards the inside and making it compress. So it will not make it compress, it is just going to reduce the tension. But here it is stretching it even more, so it is going to increase the tension over there. So this T dash will not be equal to T. But if it is frictionless, if there is no friction and there is no force on the rope from the ground, then your T will be equal to T dash. Your T is equal to T dash. Hence, whether it was a pulley, whether it had an action of rotating or not, it doesn't matter if it is frictionless. Fixed pulley, frictionless, it doesn't matter, it is having mass. If it is having mass, then the weight of the pulley will be taken care by where it is fixed. So the mass of the pulley doesn't matter. Frictionless is what matters and which makes the tension on both sides same. So if it is frictionless, then T and T will be same, otherwise not. So the friction is to ensure that the tension on either side of the pulley is same. So I'll repeat that. Frictionless means frictionless pulley means tension in the same string on either side of the pulley is same. Meaning to say, if this pulley is frictionless, then this tension is going to be that tension. If this pulley is frictionless, then this tension is going to be that tension. These two tensions are going to be same, irrespective whether they were having mass or not. Now, in questions you would have heard that they have given massless pulley also, not only frictionless pulley. So why mass of a pulley has an effect? So where do mass of a pulley come into action? So then this is the situation which I have discussed while discussing some problems earlier. In any part of a question, if you have a pulley which is movable and the weight of the pulley is not taken care by something where it is attached to, then mass of the pulley is going to play a role. So what happens is, if you had tension over here, say T and T, the tension towards the down, you can't simply write it as 2T. We'll write it as T dash and we'll see whether it is 2T or not. Now, if the pulley is going down or up, any one direction you can take, you'll have to write the F is equal to ma equation for the pulley. And when we write that, say A is the acceleration, what do we get? Downward force was T dash, upward force is 2T, is equal to mass of the pulley times acceleration. That's the acceleration. So what do we get over here? We know that it is accelerating. The pulley is accelerating. So acceleration is not zero. It's a movable pulley. It is either going up or down. Acceleration is not zero. So what we get over here is that if there is a mass to the pulley, then this term will have some value. If this term is not 0, if this term is not 0, then T dash is not equal to 2T. Your T dash will be 2T plus the term. Hence, if it is massless, then only you can take it as 0. Now, suppose the third scenario. So this was your scenario number 1. Scenario number 2 is this one, where it can be a massless. When it is a massless pulley, then you have T is equal to, for massless pulley, T dash is equal to 2T in such a system. Now suppose you have a pulley with mass, but it is frictionless. And you have a pulley with friction, but it is massless. What's the difference? So let me see. Let me analyze that. So your number 2 situation is one of the cases where it can have mass. So the pulley is having mass. So this case 2 was extension of case 1. It is frictionless pulley and is having a mass in this case. So frictionless is basically meaning that the tension on both sides of the pulley will be same on the same string. And if it is having a mass, you'll have to do the F is equal to ma for the pulley also to get the tension on the other string. Now, if a pulley is having friction but it is massless, then what happens? So I'll discuss a case where you have friction but massless. Now to discuss this, let me take the ultimate case of having friction as well as having mass. And the weight is borne by the wall. So suppose you have a pulley which is having a mass, which is having friction also, and you have a rope which is going over the pulley from this side to that side. The rope is going over the pulley, and say the rope was going this side, the whole motion was this way down. So what we have over here is we have tension on one side, tension on the other side. Maybe this tension is not equal to that tension, so I'll put a T dash, and let us discuss what is happening over here. Now, if the rope is going down, first of all, T is going to be greater than T dash, then only the rope is going down this way, then only this pulley would be rotating in that direction. And why has the pulley started rotating? Because there was friction. The friction causes the rubbing, and the friction, even if it is not rubbing, it is static, it is going along. The friction is making the pulley feel a force along the circumference, and the pulley rotates due to that friction along the circumference. So the pulley has rotated. So what can be said is this friction must be equal to the difference in the two tensions over here. So if you have a fixed surface and you have a rope going over it, have tension on both sides, then if there is friction as explained over there, if there is friction, then this tension would be less than that tension, and the difference would be, the rope is going that side, the friction is this side, then the difference in the two tension is going to be the friction. So T minus T dash will be F. You think over it a bit, and when we are doing rotation, we'll be discussing it in a more detailed way, because we'll be solving it mathematically. Okay. Now if it is going to rotate it, then this mass will start having some kinetic energy. Some work has been done over here. Some work loss in the overall system has happened because this has started rotating. So if the pulley is having a mass and it is rotating, that time we can say that there was a substantial amount of difference between T and T dash, because that will take that much of effort to rotate it. So if the mass is present and the pulley is having friction, if the mass is present, the mass is rotating. If the mass is rotating, then the difference between T and T dash is substantial, which is the friction. The friction is substantial when it is having a bigger mass. If the mass was very low, if mass was tending to 0, if the mass was almost equal to 0, then what is going to happen? Even the big rotation will be caused by a very, very small friction. Very small friction can make it go very high. So if the friction is very small, this F becomes very small, because ultimately this is going to rotate with the speed of the string itself. So whatever is the speed of the string, it is going to rotate with the same speed. So to attain that speed, you require very low friction. Very low friction is required to attain that speed. So if this is low, then your T will be almost equal to T dash. So meaning to say that even if it is having friction, even if the wheel is having friction, if mass is equal to 0, your T will be equal to T dash, because the difference amounts to the effort in rotating it, but the effort in rotating it will be 0 if the mass is 0. So there will be no difference. I'll just repeat. The difference in the tension amounts into the effort in rotating the pulley. So the effort with which the pulley is rotated also corresponds to how much of mass is there. If the mass is 0, then the effort required to rotate is almost 0. If the mass is almost 0, then the effort required to rotate is almost 0. That means the difference in the tension will almost be equal to 0. So the difference in the tension is the friction. Friction is the cause why it rotates. Friction makes it rotate with whatever speed the string is going. So the friction required will be almost 0 if the mass is 0. And the exact formula for that we'll be doing when we do rotational motion. So what do we have over here? For a fixed pulley, even if it was having friction, even if a fixed pulley is having a friction, tension on both sides will be 0. So that is what I'm going to write over here. So what do we have over here? What we have is, for a frictionless pulley, if there is no friction, then tension on both sides of the pulley, whichever setup, whether movable or non-movable. If it is a frictionless pulley, tension on both sides are same if it is frictionless. If the pulley is having friction, whether movable or non-movable, if the pulley is having friction, then the tension difference can still be 0, means the tension on both sides can still be the same if the pulley is considered as massless. So when they say massless, then you don't care whether they were having friction or not. When they say, so massless takes care of an ideal pulley in all scenario. Like in a movable pulley also, if it is massless, then the tension on both sides will be same because of the reason told to you, and it will not have and the T and T over here will produce 2T over here. So massless is what we want. So massless is the main word, massless. In such a case, we don't bother much. If the case is of a massless pulley, then nothing to bother. If it is a case of a frictionless pulley, then if it is frictionless, then in a movable pulley, if there is mass, we have something to bother. So that was written over here. If it is frictionless but having a mass, then we have to bother in this situation. If it was massless and having friction, we didn't have to bother in this situation. Massless with or without friction, we don't have to bother. We don't have to bother with or without friction. So if it is massless, whether you have friction or you don't have friction, if it is massless, whether you have friction, you don't have friction, it's the same, and it behaves like an ideal thing if it is massless. If it is frictionless, then the tension on both sides will be same, but the tension which is in the other string may not be 2T if it is having a mass. So if it is frictionless and not massless, we have something to bother. So for massless, we have nothing to bother. For frictionless with mass, we have something to bother. But we don't have to bother about the tension on both sides. So if it is friction, having friction as well as having a mass, then the tension will also be different, and this tension will also be different. The tension in the same string will be different, and the tension over here will not be a simple addition of this tension and that tension if you have mass as well as friction. So that's what I wanted you to know about frictionless and massless pulleys. Please remember these points. Please remember what is there if there is zero mass, what is there if it is, what does frictionless means, and what is an ideal scenario. Massless is an ideal scenario with or without friction. So it is like if you have a plastic kind of pulley, then it is having very less weight compared to the things it is going to lift. Then let it whirl around as much as possible, let it spin as much as possible with whatever speed. It is not going to change the tensions on both sides, and even if it was a movable pulley going up and down, the mass of the plastic is not going to matter much. So massless pulley is an ideal pulley. Frictionless pulley is not an ideal pulley if it is having a mass. Frictionless pulley is ideal even with mass if it is fixed. If frictionless pulley is fixed, then even with mass, it is an ideal scenario. Because if the frictionless pulley is fixed, then the weight is taken care by the wall, and if it is frictionless, then the tension on both sides will be same. So frictionless fixed pulley, I may add over here. Massless pulley in all cases it is ideal whether it is having friction or not. Massless pulley in all cases is an ideal scenario, and fixed frictionless pulley is ideal even with mass. So if it is frictionless, even if it is having mass, it is not going to rotate. So the T on the either sides are going to remain same. So fixed frictionless pulley may have mass. Fixed frictionless pulley may have mass, and it is like ideal. And a massless pulley, whether it is fixed or moving or whatever, it is ideal in all cases. So I hope you have got an understanding of this. I would like you to do this question now to end this session. So we have two pulleys having masses, both are having masses of 2 kg and 2 kg. Both the pulleys are frictionless. Both of them are frictionless. And you have to find the acceleration of the two blocks. So do it fast for me. So I hope you have got it right. So we have, say, tension T all over, the same rope. So T all over, it's same on both sides of the pulleys because it is frictionless. Because it is frictionless, it is same on both sides of a particular pulley. This is a new rope, will have a new tension. So I'll call it as T dash and T dash. And this time I'm careful not to write it as 2T straight away. Why? Because this pulley is having a mass. Now to solve it, I can solve it in two ways. One, I can take these two as a single body and solve it, or I can take it as two different bodies and solve it. As when we had started the lesson, we could have solved when two blocks were there in a horizontal thing with a horizontal string attached to them. We had solved the question with taking both the blocks together as well as differently, getting the internal tension in both cases. So we can do both ways. So first, let me write the equation over here for this body. So you have a weight of 4g acting down. And which way shall we consider the body is going? So if you have a 4g, if I just stop it, I have 4g, I'll have a tension of 8g over there, 8g. And this is 2 plus 3, 5g, weight is 5g. So you have a tension of 8g in a standing scenario. That means it is going to go up when I leave also. If the tension will get relieved a bit, so but still the thing will go up. So we'll take the acceleration downwards and not in the wrong way. So what do we have over here? 4g minus t is the forces on this body, results into acceleration of the body. Say A is the acceleration of the body and mass of the body is 4. That is your equation number 1. Now for this part, I can write it in two ways. So equation number 2 can be written in two ways. We'll use any one method to solve it. One way is, that is the better way to do it quickly, is taking both of them together. So what is it? Both of them, it's a 5 kg thing. Then what's the external force on it? 5g is the weight. 5g is the total weight of this. And 2t is the pull upwards. And ultimately it is going up. So what do we have? 2t minus 5g is equal to the total mass, which is 5, times what is the acceleration upwards? It will be a by 2. So shall I write it as 2a over here? I'll write it as 2a over here as the acceleration of this. So we know the constraint. If it moves by a, it will go down by 2a. So we'll write it as a. So this pulley and this thing goes up by a. If this goes up by a, this goes down by 2a. So we have two equations and two unknowns can be easily solved. Just double the first one and add to this, t will be gone and you'll have your answer. So when we do that, what do we get? So just mentally do it. You have 8 over 8g over here and 5. So 8 minus 5 is 3g. So you have doubled this. So this becomes 16 now. 16 plus 5 is 21a. So what you get is a is equal to g by 7. That's a ratio of g. That means it has to come as a fraction of g. It is coming. Your 2a is also going to come as a fraction of g, which is going to come as 2g by 7. So we are all good. It can't be going with higher than g acceleration. That's a basic cross check. So that's your answer. Now what is the other way of writing this side of the equation? By writing the equation for the pulley and the mass separately. So if we write the equation the pulley and the mass separately, we have to write the forces on the pulley separately and forces on the mass separately in two different equations. So what are the forces on this pulley? 2t up, it is going up. So I'll write 2t first. So 2t up. Then this t dash is pulling it down. That was in orange. That t dash is pulling it down. Plus it will have its own weight. The weight will be 2g. So that's the mass. 2 is the mass. So 2g is the weight. So that is again downwards. So I'm sorry, minus 2g. So that's the weight downwards is equal to, so 2t up and the weight and t dash downwards is equal to mass into acceleration. So how much is the mass? 2 is the mass. What's the acceleration? A is the acceleration. So that is your equation 2.1. And what about the equation for this 3 kg mass? The equation for the 3 kg mass, which is also going up, would be upward force is t dash must be more than the downward force, which is the weight, which is 3g is the weight, results into acceleration of the mass. So acceleration is a, it is going along with the pulley up, it is same acceleration a, and the mass is 3. So that's your equation number 2.2. So we have got now 3 equations, the first one here and then this and 3 variables. What are the 3 variables? T, t dash and a, and 3 equations. So what is the way to do it? Eliminate t dash first, get done with t dash first and make 2 equations, 2 variables. So how do we do that? We add these 2. So when we add these 2 equations, your t dash is going to cancel with minus t, and what you will see is that you get 2t minus 3g minus 2g, which makes it minus 5g, is equal to 2 plus 3a, which is 5a. So ultimately you are going to get the same equation. Then you solve this equation with the first one and you are going to get the same answer. So what's the benefit over here? The benefit is you can find out the tension if it is required in the question in this string also. So that is how you deal with questions where the pulleys have a mass. So hope it helps you. Do some practice on such kind of questions. If you have any doubt, ask me. Bye bye.